Lesson 7.4 is complete, concise, and consistent representation. So we're going to continue to talk about different representations of probability. So we've talked about our text or our written representation of probability. So probability of event A is equal to 1/5, probability of event B is equal to 2/5. And we've also talked about representing it using Venn diagrams. So we're going to add on to these and talk about more ways that we can represent probabilities. So this is a tree diagram. It's a way to represent all the possible outcomes in an event, with each branch representing combined events. So for example, if you have an event A here, the probability that A happens would be 1/5. The probability that it doesn't happen would be 4/5. And then given that A happens, there's this other event B happening. So the probability that B does happen would be 1/3. The probability that B doesn't happen would be 2/3. And then same thing down here, if A doesn't happen, what's the probability that B does or does not happen? So we can look at combined probabilities of A and B based on this tree diagram. So a box in an electronics store contains 9-volt batteries of different colors. There are 5 red, 6 blue, and 7 orange. 2 batteries are chosen to power up a radio that requires 2 batteries. So first thing we want to do is represent this situation with a tree diagram. So here's our first branch of our tree diagram, so representing the first battery that's chosen. You could choose either a red, a blue, or an orange, and then you have the probabilities of each of those three. So for probability of red, it would be 5 out of 18, probability of blue would be 6 out of 18, and probability of orange would be 7 out of 18. Now we're going to keep that battery out because we're going to use it, and then we're going to choose a second battery. So go ahead and pause the video and try and finish the second branch of our tree diagram. So the second branch of our tree diagram, they're going to be similar in that no matter which one you pick on the first one, you're still going to have 3 options, red, blue, or orange for the second one, but the probabilities are going to change. So for the red, if you picked a red first, you keep that one out, so the probability that the next one is red, well, one of the reds is gone and one of the totals is gone, so that drops down to 4 out of 17. If the first one you chose is red, you keep that one out. The probability that the next one's blue, there's still 6 blues, but now there's only 17 total. And then same with orange, there's still 7 oranges, but there's only 17 total. If the first one you pick is blue, then the reds don't move, there's still 5, but out of 17. Blues, you use 1 blue, so now there's only 5 blues out of 17, and orange is still 7 out of 17. And then if the first one is orange, you still have all 5 reds, so 5 out of 17. You still have all 6 blues, so 6 out of 17, but you lose 1 orange, so the orange goes down to 6 out of 17. So this is a tree diagram that represents this situation. So using this tree diagram, we want to find the probability that both batteries are different colors. On this one, the order actually does matter on which battery you choose first. So let's just start by finding the probability that the first one you pick is red and the second one you pick is blue. So go ahead and pause the video and find the probability of red and blue. So the probability that the first one is red and the second one is blue, well, that's the probability that the first one is red times the probability that you pick a blue one given that you've already picked a red one. So that's this first branch and then to the blue. So 5 out of 18 times 6 out of 17 is 30 out of 306. So this is one way both batteries could be a different color. Now you have to find all the different ways that the batteries could be a different color to find the probability that both batteries are different colors. So go ahead and pause the video and finish this problem. So I went through and I found all the probabilities of choosing 2 colors. So the next 2, I found the probability of blue and the second one being red, and then blue and the second one being orange. And so you get 30 out of 306 and 42 out of 306. Notice that this one, the order, even though it's a different situation, the probability ends up being the same, but you have to take both of those into account because the order matters. And then same thing here, the probability of orange and red and the probability of orange and blue, they're the same as the ones up here, but order matters, so you have to take both of those situations into account. So the probability that you pull 2 different colors is all of these added up, so 2 times 30 over 360, or 306 plus 2 times 35 over 306 plus 2 times 42 over 306, you end up with 214 different ways you can pull 2 different colored batteries out of this box, out of the 306 total ways you can pull out 2 batteries, which ends up being just slightly under a 70% chance, 0.699. So on this one, the tree diagram really helped us situate like the different situations, and even though that you're pulling like a red and an orange, it's two different ways that it could happen because the order matters. So that's why the tree diagram helps us keep it organized. So on this one, we have a partially filled out tree diagram. So it says that Mark buys his t-shirts from exactly 2 suppliers, 2AT and Net Shirts, and he buys only 2 colors, gray and blue. He buys 73% of his shirts from 2AT, so that shows this 0.73 right here, and 16% of his 2AT shirts are gray. 80% of his Net shirts are also gray, so that's all filled in. And then we want to finish filling in the tree diagram, so remember that all probabilities have to add up to 1. So go ahead and pause the video and finish filling out the tree diagram. So remembering that any one branch of the tree diagram has to add up to 1, we know that if 73% of his shirts come from 2AT, then 27% have to come from Net Shirts. Of his 2AT shirts, if 16% are gray, then 84% must be blue, and of his Net Shirts, if 80% are gray, then 20% must be blue. So given this tree diagram, Mark's going to randomly pick out a t-shirt in the morning, and we want to know the probability that that t-shirt is going to be gray. And then given that Mark chose a gray t-shirt, we want to determine the probability that it was supplied by Net Shirts. So you might need to use one of your formula from the 7.3 to help you with part C. So go ahead and pause the video and do parts B and C. So for part B, we want to find the probability that he pulls out a gray shirt. So the 2 ways that can happen is that he pulls out a shirt from 2AT that is also gray, or he pulls out a Net Shirts that is also gray. So the probability that he pulls a gray shirt out is the probability that it's 2 and G, or plus the probability of N and G. So then I calculated the probabilities of these ands here. So the probability that he pulled a 2AT shirt out is 0.73 times the probability that it's gray given that it's a 2AT shirt is 0.16. And then I added that to the other situation, which is the probability that it's a Net Shirt, which is 0.27, times the probability that it's gray given it's a Net Shirt, which is 0.8. And so you end up with basically a 1/3 chance, 0.3328, that if he just randomly pulls out a shirt, it's going to be a gray shirt. Next, it says, given that Mark chooses a gray shirt, so we know he chose a gray shirt, we want to determine the probability that it was supplied by Net Shirts. So in 7.3, we said that the probability of a given, so N given G, is equal to the and divided by the probability of the second one, so the probability of N and G divided by the probability of G. So the probability of N and G is going to be the probability of N, 0.27, times the probability of G given N, so 0.8, and then divided by the probability of G, which we just found in part B, 0.3328. And so you end up, if you know it's a gray shirt, the probability that it's by Net Shirts is 0.649. So this has been tree diagrams and using tree diagrams to find combined probabilities. Specifically looking at these given conditional probabilities, when you know that one thing happens, being able to find the second thing, and also being able to combine a bunch of these together. So different situations like a gray shirt, what are the different ways that you could pull a gray shirt, what are the different ways you could pull 2 different colored batteries, and having to combine all of those together to find a larger probability.